Okay, hello everyone. Welcome to Skill Up and Network Orlando. This is our PQC event, Post-Quantum Cryptography event, where we are talking about NIST, National Institute of Standards and Technology, finalized cryptography algorithms. All right, so first to talk about Skill Up and Network Orlando, we are a group of professionals and entrepreneurs committed to personal and professional growth and networking with like-minded individuals. So whether you're looking to grow your network or strengthen your professional and personal skill set, this group is one for you. If you need to scan our QR code, you can have access to our website and our meetup. All right, so let's just get straight into it and meet our panelists. If you would like to introduce yourself.
So hello everyone. My name is Galen Holland. I have a background in electrical engineering. While I was in college, I was studying AI as well. And right after I graduated, I went and started working for a small startup company. And they did some work about with the intersection of AI and encryption. And so we got to work on a lot of very interesting research there. So that was a lot of encrypted AI. We got to deal with AI that operated on encrypted data. I got to develop a few encryption schemes that use the mathematics behind AI, as well as a lot of cryptographic primitives. And so those were, functioning, but they wouldn't be put in any NIST standards anytime soon.
All right. And what about you, Dennis?
Hi everyone, my name is Dennis Houlihan. So I'm currently a data scientist at the Department of Management Services in the state of Florida. Previously, I was a PhD student in physics. I got my master's at Florida State University. There I was, my research was in experimental nuclear physics. So I was studying nuclear structure of heavier elements in the periodic table. So yeah, I mean, through those experiences, I have a lot of experience in machine learning and modeling and data processing and things like that. So.
Okay, and just to briefly introduce myself, my name is Arwa Morontoduhajalade. I am the event organizer for Skill Up and Network Orlando, PyData Miami, and Miami Machine Learning. I am a graduate student at the University of Maryland Global Campus. I'm studying data analytics, and I finished my bachelor's in computer science. So this is the panel, and we're ready to get straight into it. So first, we're going to talk about post-quantum cryptography algorithm categories. So the first we're going to tackle is lattice-based cryptography. So Galen, if you want to briefly introduce that category.
So that's a category of cryptographic primitives that are based off of usually the learning with errors problem, or that'll be the shortest vector problem, like trying to find shortest vectors within a very high dimensional lattice. And so a lattice essentially is you can think about it as like a chessboard almost, in which you're able to walk in between the squares, but not on the squares directly. And so if you have an infinite series of numbers or like a matrix, an infinitely large matrix of numbers, then you're only allowed to walk on certain areas within those numbers. Then that is essentially a lattice. It covers the entire space, but it's, you're kind of jumping around a little bit.
Okay, thank you for that explanation. Next, we're going to go into the code-based cryptography category.
So code-based, cryptographic primitives. So those are based off of error-correcting codes, as what they're referring to there. So that essentially means that you, as you encrypt, you create a short, a short message or a short code essentially that you attach to your encryption, and then the decryptor will be able to, based off of the mathematics behind it, they'll be able to take that code and they'll be able to work backwards and verify that, that was a message that you sent, essentially.
Let's move on to hash-based cryptography.
So hash-based cryptography, this is, I would say one of my favorite forms of cryptography because it's very easy to kind of, go over, essentially. But essentially hash functions are one way. They can't be, you can't go backward with them. And so the idea is that any input that you give a hash function, you will get a specific output that corresponds to that input. And so for the example of like password managers, let's say you have a password that you want to keep secret, but you want someone else to know that you know the password and you're verifying that it's you. So you can take your password, you hash it, and then you send the hash to the other person. So the other person will hold on to that hash. And then when you want to verify who you are with that person again, you say your password, you hash it again, and you send it back to them. They can check the two hashes and they'll see that they are the same. And so they'll know that you sent the same password without knowing what the password was exactly. And since it can't be done backward, someone cannot take the hash and go backward and derive what your password was. And also, if you have like the same password and you change it by one letter or one number, you end up with a completely different, very far away hash, far away within the space, essentially the encrypted space. And that's usually measured with what's called like a Hamming distance.
All right. Isogeny-based cryptography.
Isogeny-based cryptography is, I would say, one of the more difficult ones to kind of explain, but essentially it's more about, the main idea is about mapping two modulos to each other, essentially. So, for example, if you were to, let's say that you had a calendar of every single day in a month, and you knew, for example, the trash pickup schedule, right? And so every Tuesday there's going to be a trash pickup. So you can essentially create a version of that calendar that says, you have your public calendar, and then you can kind of create your own version that says, every Tuesday or every seventh day is a trash pickup day with some offset, right? And then if you have different types of trash, then you can say every 7 days is one type of trash, and then every 7 days with a different offset is another type, and so on and so forth. And someone else can essentially take a portion of that mapping that you create, and then they can kind of derive their own or they can apply their own transformations essentially onto that calendar, and then you can come up with a shared calendar, so to speak. And so that would essentially be your shared key that you would encrypt with.
All right, so we can move on to multivariate cryptography.
So multivariate cryptography is mostly signatures. There's a few key encapsulation methods, but it's based off of solving, NP hard problems, and we don't have a lot of like reliable algorithms for it. So essentially, it's based off of very, very long, very long like multivariable equations that can have 250 different variables or even more. And then you kind of, you have a handful of these, and then you essentially try and, the difficulty of trying to solve them increases exponentially. And that is essentially where it derives the security from.
All right, perfect. Thank you for the breakdown for our categories. And now we can move on to our NIST finalists. And we are focusing mostly on lattice-based cryptography today because the two main algorithms that are NIST finalists are lattice-based cryptography algorithms. So the first is Kyber, also known as ML-KEM, KEM. The first question is, how is the Kyber algorithm constructed?
Yeah, so the ML-KEM is module lattice key encapsulation method, is what that kind of means for everybody out there. And so a very high-level overview of how Kyber is constructed is essentially you have three parts. You have the key generation part, you have an encapsulation, and then you have what's called a decapsulation. And so when you're doing the key generation with Kyber, essentially you are doing a lot of very heavy math behind the scenes to create a public and a private key pair. And so you take your private key and you hold on to that and you share your public key with anybody. And so someone else can, for example, if you wanted to create a shared key with somebody, you could take you could encapsulate your public key, and that would create a cipher essentially, and a shared key. And then you can share that with somebody, and they would, take one of their keys, and they could do a decapsulation. So that would take their, that would create their private key, and, they would take your key essentially, and then they would be able to create the same shared key as you by working backward from the ciphertext that you provided.
Understood. Okay. Okay, so next question is, how does the encryption-decryption methods work? And I think you already kind of explained that in your breakdown of the algorithmic construction. So we can move on to crystals dilithium, ML-DAS. And the first question is, what is the crystals dilithium and how does it differ from Kyber?
Yeah, so the main difference between dilithium and Kyber is really the math behind it. So Kyber, it'll take this like large matrix and then multiply it with like basically like a secret vector within the I have to check my notes for this. The polynomial ring is what it's called. And so essentially you have this very complicated polynomial. You do a modulo on the coefficient in front of the polynomial. And then with Kyber specifically, you're doing sort of a modulo on the exponent as well, on all of the variables inside of it. And so you have this, the math behind it is that you have this large matrix, and then you multiply it by a secret vector that you generate within that space. And then you also have a error vector that you generate on purpose. And you add that to the result, and then you can kind of share that because you have that error vector, and because it's kind of lattice-based, like what I was going back to with the chessboard, that error vector kind of obscures exactly where you are in that lattice, and so that makes it very hard for someone to try and work backward and determine exactly what your secret vector was. Whereas you compare that to dilithium, you're generating two secrets and you're not necessarily adding them together. You'll multiply the matrix by one secret, and then you'll have a second secret as well, and then you can kind of work from there to create your signature. The other main difference I would say is that outside of the math, the main difference really is the implementation. Kyber is a key encapsulation method, so that means that you're generating keys, and then with those keys, then you can do a encryption and decryption of your messages. And so that would be using something like you could use Cha-Cha, or you could use one of the other methods that are out there, whereas dilithium is a signature, so that allows you to essentially verify that any message you send came from you, and that allows someone else to verify that that message came from you, and there's no way for somebody to try and come in and create a false signature because only you have the secret information that you need to create that.
Perfect. Thank you for that breakdown of the differences between Kyber and Dilithium. Our last question for this section is the dilithium optimization in embedded environments and its impact in securing the Internet of Things. So if you could just briefly explain that.
Yeah, so dilithium is already fairly well optimized, I would say. I think in order to kind of further make it more applicable for edge devices, you would kind of need someone with a very, very strong, deep math. Well, you would need a couple of math PhDs in 10 years, essentially. And so, once you have that, then maybe you could find some sort of shortcut within the dilithium process that doesn't compromise the security. But as far as deploying it on an edge device, for example, it's not super intensive. I think the largest file that you really need to work with is like a kilobyte. And so most edge devices are well over that. And then on top of that, they'll probably be able to handle the computation and most likely a couple of milliseconds. You're not really on the range of microseconds as a lot of people would like, but you are in that millisecond range, and that's still sub half a second, and so that'll be fairly fast.
Okay, thank you for explaining how dilithium is fairly optimized already and how the differences in further optimization wouldn't add to the conversation at hand. Dennis, is there anything you wanted to add to this section before we move on?
Not much. I'm not the cryptographer. My role
Yes, you're
here
the application,
applications and stuff.
right?
But yeah, that was something always an interesting topic, I guess, is the Internet of Things and how you talk about like digital transformation and kind of getting things into the digital world, but now we're going to the quantum, and how do we kind of integrate quantum machines with digital machines? That's always an interesting topic, but it seems like it's well, at least in this case, not too difficult.
I think we are making great leeway with the conversations at hand with dilithium and Kyber, especially now that they're finalized and we have a process, somewhat of a process and transitioning. And with that being said, we're going to move on to our analysis section. So now we're going to start talking about NIST standardization. And so our first question, can you explain the purpose of NIST standardization and its impact on the record-now-decrypt-later threat?
Yeah, so NIST, I believe they kind of, have a lot of, or, like a mission purpose statement, and it's more or less along the lines of kind of essentially getting all your ducks in a row, so to speak, and essentially making sure that everybody who develops, or tries to secure their technology cryptographically is kind of on the same page, more or less. And so that's because realistically, you could kind of, have any way, like anybody could really make up a cryptographic like scheme. And so NIST essentially is the government agency, I would say, that kind of comes in and says like, all right, these are good, these are not good. And so, companies should be using this and they should not be using this. And so as far as the record now and decrypt later threat, that's something that is, I mean, it's on the mind of everyone, I would say. It's very difficult to prevent, essentially because the whole threat is that somebody could capture all of the data that you share right now. And let's say you've secured it with, not Kyber, but something like SHA-128, for example, right? And so with, with Shor's and Grover's algorithms, right, you can kind of cut that in half when you move to a quantum computer, right? You're able to cut in half the time that it takes to search the entire the entire space and find the hash essentially that matches if you're trying to secure your data with SHA-128, right? And so SHA-128 is a hashing function, and like I said, with a hash you can't go backward. And so what you can do is you can try and determine what someone's password is if you have their hash by going through and checking every single possible password that could occur. And so when you check every single password, you generate a hash. You tried like 0, you check the hash. You try 1, you check the hash, and you do this, on and on until you eventually get to what the person's password is, right? And so the SHA-128 refers to 128 bits of complexity, which really just kind of means how large the hash is, essentially. And so, there's a couple of quantum algorithms that allow you to, the hash size, right, that kind of tells people essentially how difficult it is to brute force or check through every single possible hash within that space, right? So if you have a 64-bit hash, then you would need to do 2 to the power of 64 checks, essentially. If you have 128, you'd have to do 2 to the power of 128 checks. And so according to a number of mathematicians and cryptographers, they say that takes more time than is feasible by an adversary, something on the scale of like multiple millions of years or more. And so when you have that 128-bit hash, that's essentially the amount of security that you need, right? And so that's why we switched to the 256, because once we realized that there are quantum algorithms that can kind of cut that search space in half, we realized that if we just essentially double it, then we can kind of get back to that 128 bits of security. And so that protects us a little bit in terms of SHA specifically and like that specific hashing function. But the record-now-decrypt-later threat really is based off of the idea that someone could capture your hash now, if you're using SHA-128, for example, and then they could wait until a quantum computer becomes available, and then they could put your hash into the quantum computer and say, this is SHA-128 or SHA-64 or whichever version is you're using, and then the quantum computer will be able to cut that in half and search the entire space twice as fast as they would or as long or as it would take compared to a classical computer now. And so, for example, if the let's say we have a quantum computer that's available to do this in 10 years, right? And it takes 50 years to search the entire space, then somebody could wait 10 years, and now it would only take them 25 years to search the entire space. And so now, instead of having 50 years of security, you have 35 years of security, right? The 10 plus the 25. And so that's kind of the essence of it. And so there's not really a necessary way around the record-now-decrypt-later threat, aside from using very large, very difficult to crack methods of encryption. It's like the old adage of how do you make SHA, impossible to break, right? You just use a 1 terabyte hash, and so it takes 38 minutes for you to get that hash in the first place, or a week, or however long it takes to get that hash. And then, it would take an impossibly long time for someone to break that hash.
Oh, you're muted.
Thank you, Dennis. So the record-now-decrypt-later threat, one thing I didn't really think of is the added additional waiting of the 10 years, because I think when people talk about the record-now-decrypt-later threat, they never talk about the amount of time we have to wait until quantum computers become more readily available. So that's one aspect that is new in a way to think about it. We still have to wait that extra 10 years before it becomes before the half of the security is taken away. So, okay, let's move on to the second question. In August of 2024, NIST finalized the first 3 post-quantum encryption standards to include Kyber and Dilithium. What do you think the transition to these quantum safe processes look like?
So I would say that transitioning to these will most likely be a lot of central central idea transitions, essentially. So how does a company operate, right? They'd have to look at how their entire IT stack is structured and then kind of work backward from there, right? Are they currently using RSA? Are they using SHA, right? And then if they're using, an RSA token or something, right? Do they want to continue using the RSA token? Do they want to, have the little RSA token badge that like rotates, every single minute? And if they want to continue using that, then are they going to switch to a very large RSA token, or are they going to, try and find a way to create a secure channel using Kyber and then email the password to somebody? And so if they kind of go in that direction, then that would be a completely different IT structure that they would need to implement, right? It's if you have the RSA token, then as far as on the IT side, you're basically just saying, we sync up the RSA token with the central computer, and then whenever you log in, you type in your password and the RSA token, and you're able to get it, right? Because the token rotates and the computer rotates at the same rate, and so you don't have any sort of you're trying to avoid delay or like desynchronization, but there's ways around that, right? Whereas if you have, it's a form of two-factor authentication. But if you have something like, Kyber, and you're trying to use Dilithium to secure, your sign-in process, right? Then that would be something a little bit more difficult for an IT person, right? They'd have to set up a way to have a user sign in using a Dilithium signature. They'd have to get their employees to set up Dilithium signatures in the first place, and that's already probably, I would say, a lot of trouble, because most people have trouble with RSA tokens, in my personal experience. So, being able to, or trying to get people to kind of move over to that would be, it's as difficult as it is to get people to move it, essentially.
Thank you for that breakdown. So we're just going to close this analysis section off with implementation costs. You spoke briefly about the transition process and what that looks like. And now I want to discuss the financial cost estimates to include hardware requirements and software and cryptographic infrastructure. So looking at the Quantum Insider report in May of 2025, they stated that US federal agencies are to transition to PQC algorithms by 2035. So just giving us an idea of what this financially means for companies and entities.
So do you mean for companies and entities, or do you mean for federal agencies? Because those are two slightly different questions.
So, I mean, you can talk about federal agencies in one half of your answer, and a quick roundup with enterprises and businesses in the second half.
Right. Yeah, I mean, the federal agency answer, I would say, is somewhat brief. The cost would be whatever the cost is. I know it's probably a very unsatisfying answer, but essentially, the federal government hires contractors to do things. And so if a contractor is charging a certain amount, then that's the amount that it costs to get the work done, right? There's not really a lot of, here or there about that kind of process. Although for, individual companies, right, companies are able to shop around a little bit more. They're able to kind of decide, right? So for example, Bank of America would be more interested in using Kyber and Dilithium than something like, trying to think of another example here, like Pinterest, I highly doubt that Pinterest would be very interested in using Kyber and Dilithium to try and secure their user accounts, right? If anything, Pinterest probably just saves the passwords as like a plain text file. I mean, there's not really a way to know for sure without checking, of course, but it's it depends on the use case, and
I'm pretty sure they use SHA.
in that case, then well, they've got 35 years of security, right?
Yeah, I think like I'm in the state government. We're not like, I don't think the government, maybe some like high level like national security type agencies in the federal government might want to implement some kind of quantum computer on their own, but for the vast majority, like state government, contract that out. We're not going to be like doing anything ourselves as far as quantum computing for a very long time. Like we're still just trying to like grapple with AI, and these tools, and there's no real not much initiatives to like develop AI within the state government. It's usually like partner with ChatGPT or Gemini or something. So I think quantum computing will probably be a similar thing. It's going to be in the private sector as the development, and like the government will fund, hopefully, like research for it, right? With NSF grants usually that's a lot for at least academic research. But I'm sure like Google and IBM, I'm sure they can get some grants as well. So that's probably the main expenses for government, is funding research and contracting it out. And contractors like to squeeze governments because they know they'll pay.
All right. All right, I think that we've covered the analysis and the cost implementation subjects. And so now we can move on to applied application. All right, and so Dennis, in the data science section, we're going to focus on machine learning. The support vector machine, SVMs, are traditionally formulated as a quadratic programming problem. Can you explain how quantum-enhanced SVM exponentially decreases runtime in both training and classification stages?
Yeah, so a support vector machine in machine learning they're typically used for classification problems. Say you have, a data set and you have some label to it, whether they belong to a certain group or something. And what support vector machines try to do is they try to take the input data, put it into a feature representation, and put it so that it can yield a vector that splits the data into two categories. So it's almost like it's trying to get, if you imagine like you had a plot and like you had two clusters of data. What the SVM is going to try to do is just try to find a decision boundary or a vector that cuts through the two, so you can classify the two. So in this case, as far as runtime, there's a lot of you can do classically to enhance the time for computation. For example, it's good practice in machine learning just do feature engineering. So for example, if I had like an input data set and it has like 100 features, or 100, I think of it like, you get a data table, right? You have columns and you have the rows. The rows are instances, columns are different features. Column could be height, weight, whatever you're trying to do. If you're getting like, hundreds of features, there's a good chance that a lot of them probably don't affect the label as much, and so it's a good idea there are a lot of techniques to reduce the amount of features that you put in, but this could, so regardless, there might be times where you have a lot of features, in which case the computation time tends to increase in the order of n squared, so the amount of features squared. So if I have 10 features versus 100 features, it's going to be, can't do the math right now, but many times slower to compute 10 features versus 100. And so what quantum QML or quantum support vector machines try to do is they try to put the features into a Hilbert space, and so that a Hilbert space is in quantum mechanics is I don't know if I want to get too much into the weeds, but basically it's trying to encode the data to put it into a quantum basis so that it can more quickly calculate things and do computations. And so instead of being on the order of n squared, it's on the order of, I think, the log of n times. So it's just on order of the log of the number of features times how many instances you have, how many rows you would have. So it severely decreases the runtime for training these algorithms, which in our case, in our day-to-day, like we're living in the big data realm. So a lot of times, so like these companies, for example, if you're Google or, whatever, you're getting constantly getting data that's, disorganized. It's a lot. And so speeding up this process would be very beneficial. So, and obviously enhances it exponentially in the runtime. So, and Galen kind of talked about how with the record now and what was the
Decrypt later.
later, yeah,
Decrypt
how
later.
that can be a problem because quantum computers can cut things in times in half. Well, here's the good side of it is that they can cut computation time in half or severely decrease it. I was gonna make a joke before with the hash keys and like I can't wait in 15 years to get phishing text messages to give them your hash key. I'm like, no. But yeah, so I mean, this is just one application for quantum machine learning. It's also still very, very new. Of course, I think the development of quantum computers in general has a lot left to go, and I think the whole field of data science really is more focused on AI and ML development right now, that I feel like quantum computing is kind of taking a backseat, and it's kind of more of like a fringe kind of thing, like, oh, okay, well, this is a cool idea. I think this could help, but there's not too many instances where people are really using it right now. There are some packages that you can utilize, like even in like Python. I think so. It's Penny Lane.
Qiskit? Like Qiskit?
Yes, Qiskit. Yes, that one is that Google or Meta? I don't know, but there are some packages that you can use within Python that you can implement quantum computing, which is pretty cool. And even though it's still quite young, we're able to use that. So
Yeah, it's been my experience that quantum computing has taken a backseat to AI. And I think that sometimes society likes to grapple with things when it's happening rather than preventive measures. So we know that this subject matter is going to become take more importance in the next 10 years. And so why not educate ourselves on it before it becomes a command in our lives? Kind of like with AI, a lot of people are like, oh, I'm losing my job, but we kind of knew that AI was going to be in our space 10 years before it became in our space, and we kind of put it to the back burner and focused on other things until it overwhelmed us, and now we're grappling with it. And that's why I think it's important for us to have these conversations. And we could talk about AI too, and how to implement AI in our everyday lives and applications of AI. But I also think it's important for us to open our minds to other subject matters that will be affecting our lives in the future.
Okay.
Okay.
I think there's also a lot to AI that we maybe didn't expect, but we didn't have like an infrastructure to kind of deal with it. So like the NIST is very interesting because it seems like it's trying to be proactive where, okay, just like how AI was like, you could cut, you can increase productivity by X amount, and that's great, but then like how does that affect everyone? And everyone's like, oh crap, some people are losing jobs
Right.
or changing jobs. we know that quantum computing can cut computation time in,
Right.
exponentially. How is that going to affect? Okay, that's great. But also,
Exactly.
like, so having an infrastructure to kind of, with the standards and best practices and things is really important, because we're not going to catch everything. You're not going to know, but having that infrastructure ahead of time to be like, okay, here's how we think is best to, rather than just kind of like, it's happening, what do we do?
Right, exactly. Talking about governance in AI, we had to deal with governance of AI infrastructure while it was happening, rather than having a proactive structure already laid out. We knew it was coming. And so I think it just reduces the amount of lives that it affects in a negative way if we already have a conversation and have an idea of how this is going to impact us and educate ourselves, right? So if we start training society and implementing quantum education into our school system, we are preparing our youth to prepare themselves for jobs, rather than grappling with, oh, I can't have this job, or I'm losing my job because of the increased efficiency in workplaces. Now I don't have a job, but there are other jobs that become available because you're skilled in the area, right? And so I think that that's why conversations like this is important. And so we can move on to applications in quantum mechanics and nuclear physics. So first question, let's discuss the intersection. We were talking earlier about quantum machine learning. And so now we can talk about the intersection with quantum mechanics. So if you can talk about some of the applications in QML to create quantum models that implement non-classical principles of quantum mechanics.
Yeah, sure. So, quantum ML in general is kind of a boost to classical ML with computation and everything to help aid these algorithms or beat these algorithms. But now we're kind of talking about creating quantum specific models. And I mean, especially in physics and things and in chemistry and stuff, you have these inherently quantum systems that are really difficult or cannot be described by classical means. So it's not just a computational thing. It's not just that it's faster, but it's actually able to, or theoretically able to, represent the system is trying to represent, where classical computers tend to fail or struggle really. So that's kind of the big, where like breakthroughs can really come, is if we can get quantum computers that are scalable and reliable, to the point where we can actually apply them to actual quantum systems and let them do what they're like meant to do, like be quantum. Like that's something that could really take off for a whole lot of fields, especially like the high energy physics, which if you ever heard of the LHC, Large Hadron Collider, that's what they're doing. It's high energy physics is like the very particle physics, like protons hitting protons and stuff, trying to like make up what's in a proton or in a neutron and stuff like that. Those are highly quantum systems, and it becomes very complicated. You're dealing with a lot of intramolecular forces and things, and it gets really weird, and it's also relativistic. So it's really hard for these our classical computers to do those types of calculations and things. So that's the kind of not promise, but excitement, I guess, with quantum computing, is being able to use it for those types of scenarios.
Thank you for that explanation. Our last question for this event is, in the case of nuclear physics, variations of quantum algorithms for state preparation has been applied to nuclear structures. And I think you kind of alluded to that in your last explanation. So can you tell us more about this? And yeah.
Sure. Yeah. So, okay. So the thing with quantum computing is it's the major difficulty is the physical, like the literal physics of it, is like, how do you make a qubit, which is a quantum bit that can be in a superposition of states, and things. And there are criteria. I forget his first name, but DiVincenzo had a list of criteria for making a reliable, scalable quantum computer, and like one of those is to be able to create an initial state for the quantum computer, and then that can be applied to problems and stuff. And that's actually a really difficult problem to have. For example, one technique that was tried, I don't know if it's actually used anymore, nuclear magnetic resonance. The idea is you get some atoms, basically, you supercool them, and then you align their spins, and then from there you can kind of use them in the algorithms. But you have to these systems are very fragile, because these quantum systems, any little energy could really throw them off. So that's like, for example, you have to freeze them to like 10 to the -3 Kelvin or something, which is extremely cold, and you have to keep them from what's called decoherence, which means like if they have outside noise from the environment, which could be heat or something, and that can like devolve their states. And that's a huge problem. I'm trying to stay on topic here. But basically, what the adapt VQE technique was used to try to fulfill one of the criteria, which is to create a stable initial state for the qubits to then be applied and scaled up to more complicated problems. So that's kind of like where we're at still. We're not really applying quantum algorithms quite yet to actual quantum systems. We're still just trying to get to the point where we can have qubits that are reliable for a long enough time to actually do these calculations. So adapt VQE, the kind of basic idea is you try to get the qubits into what's called an ansatz, which I don't know, I think it's German, don't know the exact, but from my physics education, it's basically not a guess, but it's like an initial starting point. And then you basically try to optimize, you use that as a starting point, and then you try to optimize the Hamiltonian, which is basically the energy of the system. And so there's like this iterative process that basically you use to then apply to an actual quantum system that you want to model or something. So a lot of jargon I threw out there. I apologize, but I guess the basic point is that we're still just trying to like make a stable system with these qubits to then apply it. But once we get that, then sky's the limit.
It seems like the major challenge in quantum computing is creating an initial state of reliable qubits to be able to implement an application.
Yeah, and like, I mean, if you look at a quantum computer, Galen, you can tell me if I'm wrong, but like most of the infrastructure is like cooling, right? Like, I think people think of like regular computers, how like if you look at the 60s, or these like computer rooms or whatever, and now it's like, oh, we just have a laptop. So that's gonna happen with quantum. It's like
that's the same problem with AI.
Yeah, I mean, like, but well, that's true. I mean, but but with this, a lot of it's just like infrastructure to keep the chip cool. I mean, the chip itself is not very big, but the infrastructure you need around it. I mean, computers have gotten smaller, but have refrigerators. So.
Okay. Interesting. Well, thank you guys so much for your expertise in coming and having this event with us. I really do appreciate it. So if there's no other statements, I'm going to bring this to a close. Thank you and have a great day.
Yeah, thanks for setting this up. I had a good time.
Bye, everybody.
All right.